Okay, everyone, we'll wait another minute or two for everyone to log in and we'll start in a couple minutes. Okay, well, I think we'll start now. We've got a lot of stuff to cover, and the topic is going beyond NISQ, or I might say life after NISQ. We've got a great panel here to talk about their views of what they think will happen. And I will introduce them very briefly, and then they'll give a more detailed introduction of themselves. So Mark, why don't you go first and tell us a little bit about yourself and your company.
Thank you very much, Doug. It's lovely to be here. Thank you very much for the invitation to speak, especially on such a high-powered group as this. Let me just share a screen just for a couple of slides, and I'm going to see if this is going to work. It might not. And no, seeing as I can't see that, let's not bother with that. Okay, my name is Mark Field. I'm a principal scientist at Rigetti. I have been at Rigetti now for 2.5 years, and I'm mostly involved with the fab and the and metrology within making our superconducting processors. More recently, and the reason I got volunteered for this, we've been looking at some of our long-term research and long-term roadmaps of how we want to scale our systems up to systems that have significantly more qubits than we currently have, and also how we would keep the fidelities, which is, I think, going to be key to this. So a bit of background on me. I trained as a physicist at Cambridge University with Mike Pepper. I'm working on single electron devices at millikelvin temperatures. And I mentioned that just because my thesis was about detecting whether you had a single electron on a nearby island in a completely separate circuit. And that has, well, unbeknown to me at the time, but it has become the method of reading out spin quantum computers since then. And so there's this sort of weird feeling of coming back to where I started. But anyway, after Cambridge and the PhD and a number of postdocs, I ended up moving to industry and industrial research. And I spent a great deal of time working on materials science, new devices within clean rooms, and then also infrared detectors, and also a lot of RF engineering. And that sounds like an awful wide area, but the common theme all the way through this is making new devices work, particularly new microfabricated devices. And so when I got the opportunity to join Rigetti, I was able to use a lot of my different capabilities, knowing how to talk to materials scientists, how to talk to clean room people, how to talk to RF engineers, and how to get the whole stack going. And so it's really been a wonderful job, because I've been able to do a lot of the things I've worked on in the past. So just to give a little bit of flavor of what Rigetti is, because I know many of the audience probably don't know us particularly well. We're a startup. We've got about 150 employees. We're based mostly in the Bay Area, where we have our own fabrication facility down in Fremont at the bottom of the bay, bottom of the San Francisco Bay. And we have a quantum computing center based in Berkeley. We've also we're just in the process of opening another quantum computing center at Abingdon in the United Kingdom, which we're very excited about. So we're a full stack quantum computing company. We do everything from the chips all the way up to the software that runs these chips. And so you're welcome to come onto our platform, which is hosted both with our own Rigetti Quantum Cloud services, where you can run on our system right now. And that's also hosted on Amazon Bracket. So you can reach us a number of ways and run quantum programs right now. And so if you're at all interested in this, I urge you to come and talk to us. And we have an exhibitor booth within this conference, and there are a number of people manning that. There are also some more videos that can go into far more detail than what I can talk about here. So you'll get some idea there. And so I think just at the end of this, I'm very much looking forward to this, because You have in myself at Rigetti and also Sebastian at Universal Quantum, you have the two platforms that you can currently really run quantum programs on. That is the trapped ions and also the superconducting one that Rigetti does. And then in order to go to larger numbers, we're going to need quantum control. And that's where Niels Bultink at Qblox comes in as one of the experts on that. And we're going to need the cryogenics for both of this. So you've got a good push and pull within this group. And so I'm very much looking forward to doing it. So back to you, Doug.
Okay, well, thanks, Mark. Since you mentioned Sebastian, Sebastian will make you go next, and you can introduce yourself and your company.
Hi, thanks, Doug. Really great to be here, and really excited about this panel. So, hi, my name is Sebastian. I'm co-founder and CEO of Universal Quantum. This is a bit about my background, which is largely in quantum computing. I have a PhD in quantum computing, and currently have a faculty position in quantum technologies at the University of Sussex in the UK. And before my quantum life, so to speak, I also spent a couple of years in business as a management consultant. A bit about Universal Quantum. Universal Quantum is a startup based in the south of London, right on the coast, Brighton, right in the south of England. And we are focusing on building trapped ion-based quantum computers, like Mark already mentioned. And our core focus is on building quantum computers that employ the required solutions to eventually actually get us to millions of high-quality qubits. So big vision there for sure. And the solutions that we're employing are really based on 15 plus years of research in academia, where we've developed a unique approach that still works at the million qubit scale, which is really crucially based on engineering solutions and technologies that are currently available. I should say, I'm not saying it will be therefore easy for us to get to millions of qubits. It's really, really hard, very expensive. But I think it's really exciting, at least for us, that we know how to get to that sort of scale. That will actually eventually allow us to unlock some of those fantastic applications that most of us are really excited about when thinking about quantum computing, and that you will have heard about at this conference so far already. So I'd keep it short. Really excited about this panel. I think it's really good and important that it's slowly becoming more mainstream to ask those tough questions about how to get from where we are right now in the sort of NISQ era to quantum computers, fault-tolerant quantum computers that can really get us into this really nice application space. So super excited to be here.
Okay, well, thanks, Sebastian. And Niels, we'll turn it over to you, and you can talk about yourself and your company.
Yeah, sure. Thank you, Doug. So I'm Niels Bultink. I'm one of the founders and the CEO of Qblox, a spin-off company from QTech here in Delft, the Netherlands. And we build electronics and software for quantum computers mostly, also a little bit of quantum internet. Where most developers around the world right now use quite rudimentary and cumbersome solutions to control quantum processors. This means duct taping together meters of electronics and meters of spaghetti Python scripts to control a handful of qubits. That's often the reality of our field. We are developing systems like you can see right behind me. This is the cluster, the Qblox cluster hardware that we have developed to solve these problems. So this rack of clusters right here is a complete solution compatible with a variety of quantum platforms like superconducting qubits, quantum dots, trapped ions. So we are taking a central position in the value chain rather than creating a vertically integrated company. So we're really a supplier to the integrators. And we are overcoming the challenges by integrating all the control technology in one modular system. And we are also creating the convenient and open source software that allows to run that in a smooth fashion. So this current rack right behind me is already directly able to control processors with roughly 100 qubits, for instance, 100 superconducting qubits. So it has a lot of channels, input and output to do so. So we have the capabilities to do simple type of quantum error correction right now. So doing simple feedback, feed forward schemes using the digital infrastructure that is on the backside of these analog boxes. And in the coming 1 to 2 years, we are scaling up this technology really to push it to go beyond 1,000 qubits. So supporting more complex protocols that can also pave the way for fault-tolerant quantum computing. So instead of doing the simple feed-forward feedback, really do quantum error decoding, the tougher tasks in quantum computing. So we're supporting NISQ applications already with the current technology, and we're kind of laying the groundwork for fault tolerance, although reaching that is quite a big step ahead in many aspects of quantum technology. So we're welcome to get more details on our company in the talk tomorrow. So I'm giving a detailed talk tomorrow, and of course there is opportunity to connect in the booth. So please connect to us, and also happy to speak to all of the great people walking around here, like this panel here today, because making technology progress really requires working together on many levels. So it's really great to be part of this panel right here. Thank you.
Great, thanks, Niels. And David, your turn now.
Thank you, Doug, and thank you for this opportunity to join the panel and talk from a little bit different perspective. So my name is David Gunnarsson, as said, and I'm the Chief Sales Officer of Bluefors. Bluefors is a company doing cryogenic measurement systems, and as most know, cryogenics is sort of an integral part of many of the quantum technologies that are on the roadmap for quantum computing. My own background is in physics. I have a scientific background in cryogenics and quantum technology. So that this is sort of a little bit like Mark said, a lot of the stuff what I did 15 years ago are popping up again. So this is, it's nice to be in a sort of a nice environment where things that you did as a researcher actually becoming to be used for something useful. So that's great. A little bit more about Bluefors and our systems. Bluefors is now already a 13-year-old company, and we have matured a lot since the startup where two founders created the company. We are now more than 250 employees, and we have delivered more than 700 systems worldwide. And of course, a lot of these systems are supporting the quantum computing community to sort of reach their goals when it comes to computation. Our systems is sort of based on dilution refrigeration. So these are systems that can take you down to a few thousands above absolute zero in temperature. So it's a quite challenging infrastructure. And of course, as the topic of this panel discussion is, how do you reach up to beyond the NISQ era? There is, of course, a lot of challenges in cryogenics, but Bluefors have been working very hard and connecting to the right partners to be able to do this scale up for cryogenics in the future. But there is many parts that needs to be put together, but I think cryogenics will at least be able to follow quite far up without problems. So yeah, thank you again for.
Okay, well, thank you, David. And finally, I am Doug Finke. I'm the managing editor of the Quantum Computing Report. That's a market analysis and news website that I founded in 2015. And I will say that over the past 5-6 years, I've just seen tremendous expansion in the capabilities and lots of developments. So I'm very excited to be in this panel because I think we'll see as much, if not more, improvements and developments over the next 5 years as we saw in the last 5 years. So for this session, I'll be the moderator. And what we will do is I will ask questions of the panelists for the next 20 to 30 minutes. At the end, we'll accept the audience questions. If you are in the audience and you have questions, put them in the chat box. and we'll address them towards the end of the session. So with that, we'll get started. And I'm going to ask a question. I'd like each panelist to answer it, which is basically, what do you see right now as the biggest limiter to creating something like a $1 million, 1 million qubit quantum computer? What is the biggest challenge that you see? Why just can't we make one right now? So again, we'll start in the same order, and I'll ask Mark to go first, and we'll continue on.
Oh, thank you, Doug. Yeah, that's a very interesting question, because it's a very open-ended one. If I start going on too long, please cut me off. I think the first thing we need to get out the way for the audience, I think everybody here on the panel understands exactly what we mean by scaling, but maybe those who are slightly new to quantum computing might struggle a little bit this, because scaling can mean two things. The first one is scaling in the sense of scaling the business, just providing more qubits. And you can do that by just providing more quantum processing units that are separated from each other. But what we're specifically talking about here, and what we're going to be talking about for the rest of this session, is actually increasing the number of qubits and their fidelities, the number of qubits you can do quantum entanglement across. So making the processor itself larger and more effective at running quantum algorithms. So if I ask myself, okay, why can't I make 1 million qubits right now? A number of things come to mind. The first part of this is the sheer number of qubits is really only part of the story. And the question here is, can you use those qubits? And this all comes down to how good are your 2Q gates? What is the fidelity that you can get across of those 2Q gates? And also, how good is the coherence? The two, of course, are linked fundamentally. So let's just take a step back and say, okay, I've got a 1 million qubit system. And let's say I'm doing this with superconducting electronics. I'm sure Sebastian can comment on how you would do this with trapped ions. Okay, so that's 1,000 by 1,000 array. Let's say it's in a nice square array on a chip. At the moment, with a superconducting system, you can do something like in the range of 100 to 1,000 logical operations before coherence just removes it's the end of the game. And so if I need 1 qubit to talk to one on the other side of that lattice, I can just about get there, but I can't really do anything with it. More importantly, as you try and use these in NISQ algorithms, what you discover is that your gate fidelity ultimately limits what you can do before the whole thing disappears into noise. And so it is those gate fidelities that you need. It's not enough to have 1 million qubits. You need 1 million usable qubits. So absolutely, we are going towards scaling there. And we are working here at Rigetti on some of the reasons why qubits decohere in order to improve our coherence times, our T1 and T2, which is a different type of T1 is energy decay from the excited state 1 to 0. T2 is the lifetime of a superposition state, and that includes sort of dephasing times as well. And we've got up to 2Q gate fidelities of more than 99%. And we're now trying to make that common across our platform. And that you're going to need that, and you're going to need better. Once you get up to about 99%, you can start getting into error correction. You probably want to be at 99.9, and that's a tough ask. One of the things we are doing here is going to a modular QPU, where we're able to have an individual quantum processor. I'm using QPU as a quantum processing unit, like a CPU. In other words, an individual chip that does quantum processing. We've now got and demonstrated where we can have multiples of this chip on a backplane and entangle gates between them. And we've demonstrated more than 99% fidelity for an ISWAP gate using interleaved random benchmarking, and greater than 98.3 on the controlled Z gate, which is critical for many applications. And so this was sort of a first out of the gate to try and figure out whether we could do this. And so we're very encouraged by that, because we can make our quantum processing units larger and larger, but sooner or later you're going to have to go to some sort of modular chip. So if I'm going to large numbers, retaining coherence and gate fidelity as the system scales, you've got much more wiring, much more energy loss channels, and you've got crosstalk problems that are ultimately going to limit the usability of this processor. So we spend a lot of time trying to make our crosstalk reduce to less than 0.1%, so we don't then have to error correct our original qubits back. Another thing which I believe a lot of people are going to talk about is just the number of control lines. It gets very large very quickly. And there are two challenges here. One, how do you keep track of what's going on so that you've got the control for all these different RF ones? And you've also got the challenge of the cooling power that you've got available in your system. Quite often the number of control lines just really exceeds the cooling power of your system, and you've got to engineer the system very cleverly in order to be able to increase the number of control lines the way you would like. And so what you're looking at now is we kind of need a way to multiplex signals on fewer lines. And industry-wide, we're beginning to see some very interesting ways of doing this. There is frequency multiplexing, which a lot of people use already. And then you start talking about active switching using cryo-CMOS. There's been some very interesting papers out of IMEC that show you can, at 330 millikelvin, you can have an RF switch that works quite nicely. You're also looking at direct digital synthesis and cryogenic CMOS. This is the Horse Ridge processor that Intel have announced that works at, I believe it's just under 4 Kelvin. And again, this would allow you to remove a lot of the control lines. However, it's still, the biggest problem you have is still getting the signals on and off the chip. And so if you've got something that's running at 1.2 Kelvin, for example, you still got to have all these lines coming down of the chip, and that is a major problem. One way around that might be to use superconducting electronics, where you could stick it on the mixing chamber. And we're starting to see some interesting things out of CQC, the spin out from Hypress, who've got basically RSFQ electronics, which may or may not, we'll have to see, they've only just announced it, but you may be able to put that right on the mixing chamber. And then there's a whole bunch of stuff of using RF over optical links. And Teufel at NIST has demonstrated some very nice qubit control using essentially taking your RF signal, putting it on optical fibers, multiplexing it, and bring it down to the bottom. Okay. The final point before I shut up is you've also got the tuning gets far more complicated. You need to tune not only individual qubits, but the interaction between qubits. And so stability of the system is important. If it goes off tuning faster than I can tune it, I've got a problem. Anyway, I've talked for way too long. Back to you, Doug.
Okay. Well, Sebastian, why don't you answer the same question? What do you see as the biggest issue right now in immediately scaling up a quantum computer to 1 million qubits?
Sure. So, I mean, Mark has already mentioned a lot, but maybe just to kind of take a step back, like Mark said as well, really what we need to be able to do is increase the qubit numbers while maintaining and further improving the quantum gate fidelities that we have in the system. That is simply really what needs to happen. Now, each platform will have their different challenges in achieving exactly that. And Mark just gave us a good overview of the challenges that the superconducting qubit platform faces there. And different platforms will have different issues. I think to not delve into too much technical detail here, it is in my mind, when I think about why not just go ahead and build a 1 million qubit quantum computer, right? It's often what people will point to are the sort of technical challenges that Mark mentioned as well. And I think this is why a different or an alternative approach is most certainly worthwhile pursuing as well, whereby if you can, you try to build a machine, a very simple machine on paper in terms of maybe the qubit numbers that you have available, but where you employ engineering solutions that fundamentally still work at the 1 million qubits, so that you maybe less run into the sort of issues of, okay, I'm pushing what I currently have available to the limit, and it's going to get really hard, and then I'm going to have to rethink and try to get across this hurdle that I have here. And this is really what the approach universal quantum is focusing on, where you would probably argue that the first machines are over-engineered for the qubit numbers that you have there. However, the solutions that are actually making up the quantum computer, you could look at it and be like, okay, actually this is in a way a unit cell of a 1 million qubit quantum computer. And I think this is what we're actively working towards, and I think that is something that that is a limiting factor at the moment, that none of us can really point to a system of saying, hey, what I have here, it's not quite 1 million qubits yet, but I just need to make more of it, or I just need to tweak these few things here. There are still fundamental bottlenecks that people need to point to, quite rightly so, that one needs to overcome. And we really hope that with our techniques in place, that we might have less bottlenecks to point to in scaling up. So I think one of those systems is for sure missing. I think the other thing is on the investment side, and one should talk about money a little bit as well, is that once you appreciate the fact that NISQ will provide limited returns. I mean, we're all hopeful that we can get some good returns there, but the great applications really do start to kick in when you get to error-corrected quantum computers at the 1 million qubit scale. And if you do start to believe into that, then you also need to start significantly investing in approaches where you can really see what those quantum computers would look like. And I think that's definitely something that I'm hopeful that we will start to see more of. I can say a little bit just on the technical side, integrating different technologies into a functioning device, and for sure for universal quantum, that is one of the challenges that we're really working on, to kind of pick solutions that on their own work very well and have been shown to work, and we need to integrate this in a unique way to make our quantum computing modules that we can then eventually scale up. And similar to Mark, a modular architecture in our view is also the only way up. So that's also an approach that universal quantum really focuses on. But the biggest limit is really, how can you look at the quantum computing architectures out there? What would they look like at 1 million qubit scale? And we need to find the solutions where you can look at it and say, yeah, I know what that's going to look like and I know how to do it. And that's really where universal quantum comes in. Okay,
well, thanks, Sebastian. So the first two respondents are from computer manufacturers. I think, Niels, you have perhaps a different perspective since you focus specifically on the control electronics. So maybe you can tell us a little bit from your standpoint what you think some of the biggest challenges are.
Yeah, definitely. So listening to Mark and Sebastian, I can almost say that I could turn the question around: what is not the biggest limit in going towards 1 million qubits? Because it's really all across the stack. We're far from there. Being it in the available qubit technologies that just sheer size don't run out of the juice of the refrigerator, but yeah, it's as well the cabling issues that were mentioned. But in really going to 1 million qubit system, the idea doing quantum error correction at this size is really an untouched area, because one of the different, there are a few key challenges in doing that from the control perspective. The first is the fact that the measurement outcomes that come from the quantum error correction, you're inferring errors from the system that you need to connect to the underlying physical errors. And doing that mapping, that is really difficult. That's a computationally very challenging task already at the level of 100 qubits. So the development of algorithms to do that job in a way that it can keep up with the speed of the quantum processor. So you really have to invent new algorithms for that. And creating the digital infrastructure that can connect this whole control stack. So we have, in that case, thousands of modules that do control operations and thousands of modules that do readout operations. And all these modules need to know from each other what they have been doing, what errors have been happening, and how to correct these. And what we can add to all these challenges, that we're creating this digital infrastructure that allows doing that. So second to the algorithm problems is just to share digital infrastructure to connect information within such a large system. And second to that was already mentioned is the level of gate fidelities that you need in these large systems. They at least have to go up by about a factor 10. The errors have to be reduced by a factor of 10 to make fault tolerance possible. So what we can do from the electronic side is create really low noise signals. We've already been addressing that partially by reducing the noise levels by about a factor of 4 compared to any alternative solution available right now. But we have to keep pushing that further to make these larger systems a reality. And then second was already touched upon a little bit is the levels of drift in the system. So quantum computers have operation time, but next to operation time, they are constantly calibrating themselves already at the level of tens of qubits, and this overhead will go up by scaling up the system. So creating control systems with very low drift that are very much controlled in terms of their thermal householding, but also the way the electronics respond to thermal drifts is very important to make these systems scale up better. And then not even yet talking about software, which is also very challenging to scale up the compilers to get to the level that they can reach the parallelism that allows compiling the circuits for these large systems. That's another big challenge that we're working on. Yeah, that's
okay. Thanks, Niels. And David, you actually have a much different perspective than all the others, since you really deal with the mechanical side of things and the cooling side of things. Do you see any, big challenges or things that your company is working on to enable some of the scale up to these very large computers?
Yes. So of course, all the other speakers have sort of exhausted the topic when it comes to sort of the core technology and what is needed. But from a cryogenic perspective, I would like to turn the question around. It's more like what possibilities there are actually to create these cryogenics, because the technology exists there, and it's possible to sort of get cooling power to sort of support something that even brute forcing to some extent. Of course, the ideas of multiplexing or putting sort of control chips at a mixing chamber, of course, will really help and not need the cryogenics to scale to the same level as it would if you brute force with a lot of wiring and cabling. But of course, this is going to be large systems from a cryogenic point of view anyhow. But I think it's good to put it in perspective. Go and look at the HPC center today. This is not small enterprises. It's huge cooling power needed already there. So I think it's going to be sort of a sort of compromise between costs, quantum advantage and computation, and the technology from cryogenic point of view, that I think will be available for 1 million physical qubits. That it's just, as Sebastian mentioned a little bit, money will have a point here at one point. How much are we willing to spend on this? I think we need to know that it will give us something. Then there is for sure possibilities.
Okay. Yeah, I think there's some venture capital sessions and some government funding sessions later in this conference. So let me ask the panelists this. When you want to do a more advanced development, sometimes it's really more straightforward engineering. You basically know the theory on how you want to do it. And it's really just a matter of just, putting in the work and doing the simulations and doing the designs and those types of things. Other times, it's you need some basic research. You really don't know exactly how to do it, and you have to do some more research to get there. And there's a number of things I think that areas where people have to work in quantum computing, including error correction algorithms, mechanical packaging, qubit implementation protocols, electronic control software, and the electronics. Of those various areas, which of those areas do you think still require some basic research as opposed to just straightforward engineering? And I'll let anyone maybe raise their hand and chime in.
I can virtually raise my hand here.
Okay, go ahead.
And say something. I mean, I think again, it's very very hardware specific, I think. Certain approaches which hold great promise going forward for sure, might just be at a different TRL level where a bit more research is required. But if they crack those challenges, then they have a very, very positive road ahead. I think for us on the hardware side, and that's for universal quantum with that approach, that there's maybe less fundamental research required on the hardware side of things. But I think in general, what we most certainly would like to see is a lot more work being done on error correction, in reducing the overheads in terms of the number of physical qubits that you need to get to error corrected logical qubits. And I think looking in particular at some of the advantages that different hardware platforms may have, let it be on the connectivity side of things. Something's close to my heart because with our sort of approach, we do have this full connectivity in our system, which we're very hopeful will have a big impact on the efficiency of error correction protocols that we can run at the end. But I think there's a lot more learning to do there, and I'm really hopeful that by the time we get to those sort of scales that we're talking about today, error correction will help us in bringing the sort of goalpost closer to us, and we can hopefully meet somewhere in the middle. That would for sure be great. And I think generally on the application space, there's a lot more work to be done. Thinking about algorithms for specific applications that maybe don't need the full-blown couple of thousand error corrected logical qubits systems. Other things that we can do with these machines early on, I think it's really important to work on as well.
Okay.
Maybe I won't give a complete list, but to give other people also an opportunity to chip in.
I'd like to add something to that.
Sure.
It's possible. So what I really like in the field right now, what is happening is the level of diversification in how we tackle problems. So what I mean with that is there's really a value chain that's being created that allows specialization on different topics. And that gives the first thing that gives you is that companies or universities can really specialize in one part of the value chain and deliver that to, for instance, system integrators. And that allows not just specializing on some topic for a company, but also it allows to really put more R&D or basic research tasks at academia and allow companies to focus on more the engineering challenges like integration that some of the companies like Rigetti are doing, but also on supplying different parts of the system like us or Bluefors, which they are doing. So the ability to really separate these tasks and work on it really on a global scale is for me a very great transition that's happening right now in the field. So.
Okay, anyone else want to address that? Yeah, go ahead, Mark.
Yeah, just a quick one. Niels makes a very good point about splitting this up into different areas where different groups can actually begin to have an effect on this. And one of the things we've been doing at Rigetti is concentrating obviously on the hardware builds. And there is no absolute roadblocks, but you keep getting tripped up by little things. Every time you make a process change, you suddenly realize you've affected your coherence. And so there's a lot of experimentation needs to be done. But back to Niels's point about splitting it up, one of the things we've been doing is trying to open up our systems to other players and getting it into the hands of people to say, why don't you go and play with this? And part of that is some of our work with Innovate UK to work on the initial parts of quantum verification and also benchmarking, and also some of the early work on quantum error control, which we're very keen to see, as Niels is. And Sebastian mentioned this, that they'd really like to see some early work on this. And I think that's going to be key. Part of what we've done is we've actually opened up our hardware so that within our system, you can specify individual pulse control. So in other words, we're not just saying, here's an RF pulse, go and use it. We've also said, here's ours, but you're welcome to make any RF pulse you like within the system. And what the hope here is this enables a new class of companies that can come in and concentrate on things like quantum control. This is something I think Qblox would be very well set up to do. There's also Q Control, Michael Biersek's company that are involved in this, and a number of others. So yes, I think you're entirely right. Okay, I'll stop talking at this point.
Okay, very good. So let me ask about one architecture question that actually came up again this morning. There's IBM and Rigetti were on the same panel, and they're talking about a multi-core type of solution, which is the Rigetti approach. IBM, for at least for a while, wants to go monolithic. They want to create a 1,000 qubit on a single chip. Do you have any comments or questions, comments on in terms of whether or not we will require multi-core technology to get to this $1 million qubit machine that I keep on talking about? I think maybe let's go to Sebastian. I think we know what the Rigetti stance is, but Sebastian, why don't you also address that?
Sure. I think, I mean, I spoke a little bit about, you know, my love in a way for this sort of modular approach going forward. And I think, you know, just sticking within one chip is fine for now, but this comes back to my point that I tried to make earlier. If you then ask the question, okay, what do you need to get to 1 million plus qubit quantum computer? And like Mark said as well, you know, you ask yourself these questions, and then you do realize that you need to have a modular architecture and think about how you're going to connect quantum mechanically individual modulates. And, you know, Rigetti's done, you know, beautiful work there, how to do that for their particular architecture. And in trapped ions, you know, we also have, you know, nice solutions in place for that. And, you know, particularly Universal Quantum, again, I don't want this to be a sales pitch at all, you know, have worked very hard on that, because you can't really be serious about, you know, getting to that sort of scale, if you do make those sort of claims, if you have not thought about, you know, how to really have a modular architecture for the platforms that we're considering here right now. So I think it's absolutely critical.
Okay. Let me ask one more question. We got several questions from the audience, but one question that I've asked, you know, a number of people, and amongst the quantum community, I see a sort of a split opinion, which is, when will we get to a point where we will be able to see quantum advantage on a real world application in a production mode? And the real question is, will we be able to do that with NISQ level computers, or will we really need to wait until we have a full error corrected quantum computer before we're able to achieve quantum advantage on a real world application? Any comments, questions? Again, you can raise your hand or speak up.
I mean, I'm happy to get my head chopped off here by probably a number of participants, but I think it depends how you define computational advantage and how far you want to push that. But I'm not super optimistic in terms of how far this can really get us. And this is really where I drive towards these larger scale systems to come from. And I think we need to be mindful that we don't overpromise with what the machines that we currently have available and will have available over the next couple of years in terms of what they can deliver. Nonetheless, it's fantastic, it's great work, and it's absolutely critical to do that work on that road to larger scale systems. But I'm not convinced that the sort of computational advantage that I would really like to see quantum computing you know, kind of bring to this world, I don't think that would happen with NISQ. That's my opinion on that topic.
Okay.
But it's yeah, I guess it's also a learning phase that. So we can. I'd like to look at it a bit more positively to keep the discussion going. But yeah, so there are definitely applications in the NISQ era. Whether they will be economic boomers and it will create a huge market, that is up for debate. But it's also the search for new algorithms and new application that has to be very iterative. So creating a larger system and letting a lot of people play with it, letting a lot of algorithm developers get excited about it, and let that side of the market also develop is very important. And we can only get there by building these systems and making them available to a wide audience. So I think that's very important steps towards creating more and better applications. So that's an important process, I would say.
Okay. Okay, well, let me turn to some of the questions from the audience. We had a very interesting one. You know, in the classical computing world, people are developing application-specific processors like GPUs and those types of things. Do we ever foresee that people might start doing that in the quantum world, creating specific quantum processors to solve specific problems?
Yes, I think so. I think you're beginning to see that now, actually. Of course, quantum computers, as we sort of talk about them, can do any application you want. They can do any computing. They're universal. But where you're really going to see advantage is in cases where you've got the algorithm scales horribly with numbers, where the sort of order, you know, n factorial problems, such as trying to do traveling salesman problems, for example, is something where maybe you can get a quantum advantage to this. There are certainly a lot of work out there. And so what I think you're going to see is the beginning of quantum processors being tailored to specific algorithms. And it wouldn't surprise me if the different approaches to quantum computing ended up being certain ones. So trapped ion computers maybe are very good at one particular one because of their universal connectivity. And maybe superconducting ones are particularly good at a different algorithm because of their very fast gate times. So you can imagine things being developed where, as far as you as a user are concerned, you're going to be completely agnostic to what's going on. But underneath on the stack, there's going to be a set of different quantum processors. And Rigetti has already made a beginning to, you know, we don't think in terms of trying to get our processors to be very good at one particular algorithm. But it has already cropped up because of the limitations of the NISQ computers. We are doing some quantum variational work with our partners at USRA and NASA as part of a DARPA program. And for that work, which is all about trying to figure out graph coloring and max cut work, you can compile that down to ISWAP and controlled Z gates. But it was going to be, you needed quite a number of them to get a large, to be able to get enough horsepower to do anything interesting as you scaled the numbers. But it became obvious during this work that if we were able to natively implement a different type of gate called an XY gate, that you could compile this down to a much smaller number of gates. And so it was going to be possible on the NISQ computers that we had. And so we went away and actually implemented that gate specifically for it. So anyway, I think the answer is yes, it's happening. Whether we end up really specializing is an interesting debate point there.
Okay, let me sort of follow that up. And this, I'm going to ask a question of David. David, do you guys create any application-specific dilution refrigerators, or just have standard models and for everybody?
So the systems that are sort of standard today, they are of course quite generic in their design. So there has been sort of traditionally been different stages where you actually have a certain temperature, where you actually draw your sort of, you have different cooling power that you can sort of lift at these stages. And that is partly arbitrarily, and that's just tradition. So there is, of course, there is ways that you can tailor a dilution cooling unit also to sort of maybe gain some advantage when it comes to sort of implementing your technology into the system. So a short answer is, of course, yes, you can do some tailoring, but the question is, will it have an implication to the technology that the other panelists are talking about? That is not 100% certain.
Okay, So one of the things I think we've already learned from this session is that not only do you have to scale up the number of qubits, but you have to scale up the gate fidelities. And we have a question from the audience as to whether or not you believe that we would be able to achieve a 99.9% 2-qubit gate fidelity on your computers. I don't think we're quite there yet. And if not, what fidelity levels do you think we will need in order to have a viable error-corrected 1 million qubit machine?
I actually think in multiple platforms already the 99.9 level has been reached or is close to being reached. But that's often in an isolated fashion. So
right.
Just a few trapped ions or a few superconducting circuit qubits together where you can reach those high numbers. But doing that in a scalable system and doing that without a lot of crosstalk, because that's a more exotic type of error that can really screw up your algorithm and quantum error correction in particular. Reducing those type of errors is also very important. But yeah, we are roughly at that ballpark, near that ballpark. So reaching those levels of fidelity is not so far-fetched. And that's also the level of fidelity where quantum error correction really starts to be fun, because if you are at the 99% level, the amount of overhead qubits that you need to get your logical qubit is huge, and by increasing the fidelity of the operation, the overhead goes down a lot. So, and those numbers, that the levels we are roughly are with fidelity, are close to already good enough. So that's not actually perhaps too far away, but yeah, we need to push it up further. That's true, but it's incremental steps. I think would be needed.
Okay. Okay, I think we could go on for hours, but we're running near the end of our time. So I will give each panelist 1 minute to sort of summarize, some of their views on this, and then we'll close the session. So I'll go in reverse order in this case. We'll start with David in terms of, again, life after NISQ. Do you have any perhaps final thoughts you want to give for this session?
So really being in the business and supporting this technology, of course, just doing the NISQ is a challenge in itself. And I think that's maybe all the other panelists can also sign up for. When it comes to cryogenics, of course, we are depending quite a lot on the development of the sort of applications that are being made. And it's hard for us to know what is important, where. So practically, where do you want cooling power? What temperatures do you need to lift most of your heat, etc.? Because these things are not really determined yet. People are working in these generic setups that I told you about earlier. So there is, from our point of view, there's a lot much to learn to understand how this whole thing scales up. But that was what I tried to answer in earlier. There is a lot of possibilities for the cryogenics, because there is a lot of solutions to actually give the user exactly what he needs. But it's just a question of figuring out what the optimal solution is there. But I think it's looking quite bright from the cryogenic point of view.
Okay, well, so thanks, David. So Niels, I'll let you have your 1 minute summary perhaps for this session.
Yes, life after NISQ. I hope to be sitting on a nice beach with a lot of the fellow engineers and business people that work in quantum computing, because there will be a nice closure. Now, yeah, there's a lot of exciting work to get there, and yeah, that's great to be doing. And it's mostly about the journey towards beyond NISQ, I think, rather than what we do after it. That's the excitement. So thank you.
Okay, thanks. Sebastian, your 1 minute summary.
Yeah, I mean, life after NISQ, I mean, this is what what drives us, right? This is when it gets really, really exciting for quantum computing. But I think we, and hopefully the attendees of today's session will have also seen that this is hugely complicated, very, very difficult. But I just want to keep reminding people it's absolutely worth it. And I think that the field has come really far in the last few years. And I think we've got a really good future ahead of us as a field as a whole. I think we just have to keep our eye on the ball and not forget where we eventually need to be. And I'm, like I said at the beginning of the panel as well, I'm really excited that these sort of panels are coming up where we do think about how to get there and what needs to be done. And I'm super excited to make it happen.
Okay, and finally, Mark, we're right at the very end of our session, so maybe just a real quick summary from you in terms of what you think about life after NISQ.
Sure, Doug.
How we'll get there.
Thank you. I think the question about can the hardware be built, I think we're coming slowly to the concept of a cautious yes. As David said, the cryogenics actually looks really quite promising. There's a lot of work to be done there, but it looks promising. Same with Niels and the control thing. You can do this. It's all, from our perspective, going to come down to gate fidelities and how we're able to scale that out. But we're also trying to keep our eye on the goal here, which is to provide a useful quantum platform, a useful computing platform. Ultimately, this has to be a business for everybody. And that means we've got to move from a physics to an engineering type of way. So this ultimately just becomes something that you don't even notice as a programmer.
Okay, well, I want to thank everyone in the audience for attending. I want to thank the panelists. It was a great session. And I think my 15-second summary is that I think the next 5-10 years will be even more exciting than it has been over the past 5 years. So looking forward, and I'm sure we'll have some great sessions also similar to this in the future. So thanks everyone, and we'll see you around. Bye-bye.
Bye.
Bye-bye.
Bye.